Welcome to Brain Vision.
Okay, so in this problem, we are dealing with the same situation as problem 41, but we're just doing a symbolic version of the problem instead of with actual numbers and values for the variables. So if you have done problem 41 already, then you've got kind of a head start in this problem. But if you haven't done problem 41 already, then I'll do this. I'll do this recording so that you can follow along even if you haven't already done problem 41. So in problem 41, or in figure 41 on your book, you have a plastic cylinder that is filled with water, and water is being pumped into it at a certain rate. We also have a tuning fork at the open end of the cylinder that's vibrating at a frequency f. So that is one of our set variables. Another one of our variables is capital R, which is the rate at which the water is being pumped into the tube. And this rate R is in terms of volume over time. So its units are volume over time. So it's a capital V. Since it can be a little bit ambiguous if you don't establish that, and that's a very important detail. And then the other variable that we also have is the radius of the cylinder, which is lowercase r. And from this, we're supposed to figure out how much time passes in between when two resonances occur. So when the water's at a certain height in the tube, there will be a resonance created by the tuning fork and the standing wave inside the tube. And then as the water rises, a little while later, there will also be another resonance. So we have to figure out what this time interval is. So the first thing that we need to do is we need to figure out what this distance in between these two water levels is going to be. So how we can do that is if we take a look at the problem, or if we draw a diagram similar to the one in the book. So here's our plastic tube. The water is at a certain height now, and it is rising. And so in order for there to be a resonance, there has to be a standing wave with the tuning fork, which is up here. There's my little tuning fork drawing. So at the open end, there needs to be an antinode in the standing wave, and at the water level, there has to be a node, because the water acts as the same way as a closed end, since it's a change in medium. So one way that we could see this happen is if the standing wave of the sound wave looks like this. I like to draw standing waves like this, where there's two ends. So then as the water rises, there will be another resonance when the water reaches this level where the blue is. So the distance that the water needs to rise is this length here. And the easiest way that we can relate that to frequency and the sound of and the speed of the wave is by making it some multiple of the wavelength lambda. So if we look at this, we'll notice that this is actually half the wavelength, this distance that I highlighted here. Because it's a little ambiguous when we draw it with two sides to the standing wave. But if we take out just one edge, like this, we see that it starts at a node, it goes to one of the antinodes, and then it returns to the node. That's only half the wavelength because it hasn't gone to the opposite antinode and then back to a node again. So this distance is actually lambda over 2. So that is the distance that we want to find in terms of these variables, F, capital R, and R. So the way that we can do that, well, lambda itself is going to be equal to the speed of the wave divided by its frequency f. And that's just from the equation that the speed of wave is equal to its frequency times its wavelength, just rearranged to solve for lambda. So then we just say that lambda divided by 2 is going to be equal to the speed of the wave divided by 2f. So that's how we can represent what our distance that the water needs to rise as using variables that we have established. So the problem hasn't said anything strange about like the temperature of the air, or like said that there is a different speed of sound in the air for this situation. So we can assume that v is equal to 343 meters per second. So the problem hasn't strictly said that we can use v. It's a little ambiguous, but since v is just a product of the medium that the sound wave is traveling in, it's it wouldn't be unusual to leave it in the solution. So I'll show both the solution with v in it and with 343 in it at the very end. So that's the distance that we need to travel. Next, we need to figure out how quickly the water rises. We have the rate of change of the volume of water in the tube, but we don't have the rate of change of the height of the water. So how do we figure that out? Well, there's actually a relationship between the cross-sectional area of the tube and how quickly the water volume is changing. So I like to call this cross-sectional area a capital A. And since the tube is a cylinder, its cross-section is going to be a circle, which means that its cross-sectional area, of course, is going to be pi r squared. And lo and behold, lowercase r is one of the variables that were given right at the beginning. So that's great. Then we need to calculate the rate of change of the height of the water in terms of these variables that we have at the beginning. So this rate of change in the height of the water, I call it capital RL, to kind of indicate it's a rate of change that's linear rather than volume over time. And I said that this was equal to the rate of change capital R divided by A. That's a pretty messy A. I'm going to rewrite that because if you take the rate of change of volume over time, and if the cross-sectional area in one direction doesn't change, then that means that the only thing that is going to change is the height, and that can give us the rate of change of the height of this volume. So the rate of change of the height of the water is just going to be equal to the rate of change of the volume of water divided by the cross-sectional area of the tube. And we already have an expression for A that just uses the variables that we're allowed to use. So this RL is going to be equal to capital R divided by pi r squared. So now we have how far the water needs to rise and the speed at which it's rising. So if we reframe this as like a kinematics thing, it's similar to saying, the equation that velocity v is equal to the distance divided by the time. So we have a constant v, which is our rate of change of the height of the water, RL. And then our distance that we're traveling is lambda over 2. So we can use it similarly to calculate the time that it takes to travel this distance. So t is equal to, t is equal to d divided by v, but in this case, our distance is equal to lambda over 2, and our v is equal to r sub l. Better. And we have expressions for lambda over 2 and r sub l that use only the three variables that we had at the beginning. So lambda over 2, of course, is equal to v divided by 2f, and r sub l is equal to capital R divided by pi r squared. And so now we can just go ahead and simplify this. So t is then equal to, so we have we have v over 2f in our numerator, and then we have capital R over pi r squared in our denominator. So the pi r squared will flip to the numerator, and then the 2f will go to the denominator. So this ends up with v pi r squared in the numerator, and then the denominator we have 2 capital R F. And that is our answer if we want to keep v into it. If you want to take v out of it, because we're assuming that the speed of sound is 343 meters per second, you can write 343 pi r squared divided by 2r, capital R, F. And I think either way works just fine. And that is how you do this problem.